Okay, let us do a review of the content that we have studied so far, and it's really mostly related to vectors and forces. So we should understand very well what is going to happen here with the concepts of forces. So we simplify systems in order to be able to study them. And this whole system, the only thing we really do is find where the forces are. So there's one force here that is pushing, or I said better, pulling the truck. There's the weight of the truck, which is a force, and there's a force and each tire holding the truck. So if we have that case and we draw it like this, we have a force like that, a force like this, and two forces like that. To be actually more precise, there's going to be a force that is friction. Okay, so the goal here is to find our system of units. The units and the coordinate system. So say the coordinate system is going to be x is positive and y is positive. To the right, positive x, top positive y. And that only really matters because we want to know where, so we can have a convention for the forces. So the summation of forces in x, and now we're going to say F1, F friction, say W, and R1, R2. So summation of forces in x will give us that F1 to equal to 0 because we're talking about statics. So F1 plus friction force is equal to, well, but this is the first thing that we have to notice. The friction is towards the left. So minus force of friction equals to 0. Therefore, in order to get this right before moving, F1 is going to be equal to the force of friction. Same thing for y. Summation of forces in y equals 0. What is W? W is the mass times the gravity. So we have R1 plus R2 minus W equals 0. If W is greater than R1 and R2, the tires are gonna break. And that happens sometimes when you put extra weight, then the suspension breaks or something. So R1 and R2 is not necessarily the force that the tire is in, it's the force that the system has to support in order for the truck to be able to stay in rest. Okay, so after saying that, we already know that we can move forces around as long as they're in the same plane. If we move forces in different planes, we can have something called moment. So, for instance, this is a very key concept. So, for forces, again, if you have a box or a truck or whatever, and you put a force here, in statics, this is the same as having the same box with the same frictions and pushing and putting the force here. These two things are the same. Okay, in other fields, it might not be the same. In vibration, in dynamics, but in statics, this is the same. Okay, so the amount of force needed to move this is the same here than here. Okay, because this is a simplification. Now, in moments is not the case. If you have, and we'll talk about that in a minute, if you have a force here, it's not the same that if you have the force here, because this distance is greater than this distance. And remember that moment is force times distance. Therefore, moment 2 is going to be greater because the distance is greater. So in moments is not the same to move the force around, but in planar forces, when the force is on the plane, it is the same. Okay, so that's another concept that we need to review. So as we said, it's equivalent forces if we have the force, as long as the force is positive or negative, whichever the coordinate system tells you, you can move it around on the plane in the same direction, so parallel to the axis. So this is parallel to x because we decided that x is positive towards the right hand side. So this is pretty interesting. So if you have a point A and point B, and P1 and P2 are the same, that is the same as having P2 exactly at point A, which that is a body of in rest. It's technically the same as having no force applied. You're just wasting energy, literally. Same is if you have a compression force. If you're compressing, is the same if you're compressing in statics. This is not the same in mechanics of materials, because here you have deformation between A and B. Here you don't. But in statics, the is in rest if you apply both cases. So in this class, for this class only, we're going to have the concept of simplifying the system where we just care about where the forces are and the direction of the forces. All right, so this is new and this is a pretty interesting concept. So they're vector products. So there are two types of vector multiplication types. There's the dot product and the curl. So let's start with the simplest one. Let's start with dot product. The dot product. Okay, so say we have vector A and vector B. And vector A has components A1, I, A2, J, A3, K, and A4, T. Let's say it has a time component. A4, T. Okay. And say vector 2 has only two components. B1I, 0J, and B3K, and A4T. I'm sorry, B4T. Let's do that better. Okay, so first of all, remember that this hat is for I, J, K, and T, means the directions. So what that means is that we have X, Y, and Z with directions I, J, and K. That simply means that the coordinate system, the X, Y, and Z will be for coordinates in units of meters, inches, whatever, and I, J, K will be for directions of vectors. so typically with units of newtons or pound force, etc. But x and I are parallel. J and K are parallel. J and Y are parallel. Z and K are parallel. And there's another fourth direction, which is T, which we will have to find out how to draw that for dimensions, but there's another one which is T hat. So A dot B is very simple. It's each component in each direction. So it's going to be AI times, or A1 times B1 in I, comma, A2 times 0 in J, that's 0 in J, comma, A3 times B3 in K. So that's why I wrote them like this, because it's easy to see what I need to do. And well, it seems like I said I was gonna have only 2 components, but I didn't. So it's gonna have 3 components, A4, B4. So this one will be 0J. So A dot B will be A1, B1 in I. Well, it's just that. We don't have to rewrite it, because this is actually the proper way to have it. 0J and K and T. So you just multiply both. You don't add, you don't subtract, you multiply both components. This is the simplest thing. This is called the dot product. And you're scaling each number by the same direction. So just a scaling factor of the vectors. Okay, now the curl product is a little more intensive. The curl product. And let's do something simple. Let's do just 3D, because it gets more complicated in 4D. So we're gonna have the same vectors A and B with components A1 I, A2 J, A3 K. All right, and B1 I, B2 J, B3 K. The curl product tells us that we have to do the following, just for 2 vectors. We're gonna place I, J, K, like so, then the vectors A1, A2, A3, B1, B2, B3. Okay, so the curl product tells us that A curl, which is an X, B equals, all right, so here we go. First, we take and hold I fixed. Okay, so hold I fixed and move, cancel that, and move to this quadrant. What I mean is, picture that we're canceling this line and canceling the stop line. So we have A2 times B3 minus A3 times B2. Okay, minus. Now we take J. Now we cancel J column and the top column, and we're gonna have A1. We cancel the J column, A1 minus B3, times B3 times minus A3 times B1, and that happens in J. All right, plus we take the third component in K and we cancel the first row and the third column, and we do A1 times B2 minus A2 times B1, and that happens in K. All right, now you might wonder, why do we have to do this? Well, the curl of a vector is, or a few of many vectors, because you apply the curl between vectors, is very useful because it gives you the rotation of the vectors. So let's go to the graph. So if you were to apply a curl between P and Q, these two, say they're forces, these two forces together will make a V component, this blue line, this blue vector, try to move in that direction. So that's why cement trucks rotate in a certain way when they're on the highway, because that rotation, that force, will make him move forward. So if you have a cement truck rotating the drum in the opposite direction while you move forward, you can actually make the truck tip over. Okay, so that's the curl. It's very useful to find forces and rotation. And just FYI, so that means that a vector A and a vector B, and if we know the angle, then it will be actually much better, because the vector V, which is this picture right here, all right, so V, which is A cross B, that is what we just did. But if you know the angle, it's very easy, because V equals, which is V, A cross B equals A times B times the sine of the angle. But sometimes it's not easy to know the angle. Okay, all right, so that's the same thing. But what if you have three vectors? What if you have A, B, and C? And this is A1, A2, A3. Let's do B1, B2, B3. So A, B, and C obviously are numbers. A1, A2, A2, they're going to be numbers or variables. Well, not in this class, but in other fields you can have a variable, X, and etc. C1, C2, C3. Okay, so we have three vectors and we want to find the curl product between them. So the curl product of those three vectors is A1, whoops, B1, C1. Wait, I'm doing this the wrong way. Let's do it like this. A1, A2, A3, B1, C1, B2, C2, B3, C3. Okay, there you go. So the curl product is the same thing. You hold A1 constant and do the same thing. That take this and that, those four elements. So it's going to be B2 times C3 minus B3 times C2, and this is in I direction, minus A2 times B1 times C3 minus B3 times C1, J direction, plus A3 B1 times C2 minus B2 times C1. k direction. Okay, so that's between three vectors. All right, so go ahead and practice that. It's gonna be a lot of work if you haven't done it before. So do a few examples and make sure you can do it properly because we're gonna use that a lot. An FYI, a rule that it becomes pretty useful is the cross product of two vectors is the same as the negative value of the cross product of two vectors. The magnitude is, okay? And just because just what it means is that the vector is aiming down instead of aiming up, but the magnitude is the same. Okay, this is what we just talked about. Well, actually, no, this is different. We have P cross product of Q plus Q1 plus Q2. You just add up Q1 and Q2 first and add the cross product, or just do P cross product of Q1 plus P cross product of Q2. And this is what we just did. P cross product Q cross product S is not the same as P, and then it's not commutative. Okay, so go ahead over and review the chapter and make sure you understand these things. I cross product I equals 0. Okay, I cross product J equals K. That's why I was telling you that you cancel out columns. And that is because this is very useful. I cross product J gives you the direction in K. But I cross product I is basically sign of 0, which is 0. So with the sign, you can get away with knowing which one is which in case you need to know which direction is positive and which direction is negative. Okay, this is basically the way that we compute I, J, and K. So, okay, so they're telling us how to do the operation that we just did. So review the book, has plenty of information. In statics, the curl is used because that's how we find the moment between vectors. So R could be the distance. A vector R could be the distance. R1, R2, R3 are the components of the distance. And F is the force. So doing this curl product, it will tell us the moment. This is what I was telling you about the cement truck example. Okay, so this is something that we're gonna have to do pretty often because the moment in vector world is computed through cross product. And the cross product is seen everywhere. So like the force that you apply horizontal or perpendicular to the blade that it makes it rotate, that is a cross product. The distance at which you apply a force, that is a cross product. Okay, that's a moment basically. So the moment has a convention, which is if it rotates counterclockwise, it's positive. If it's rotating clockwise, is negative, meaning that if you apply a force to a wrench, or a screwdriver or whatever, and this is rotating clockwise, okay, this force is negative. This is a negative moment. If it's rotating counterclockwise, that's a positive. It's a positive moment. Okay. All right. So we'll have some homework about this. We just want to make sure we understand. And of course, the force could be anywhere, any type of magnitude, any type of direction. Here in this case, different forces will apply different moments. Let's borrow this for a second. Okay, so say all right. Let's say that this is z direction. So the r vector, remember sometimes r is with an arrow, this means vector. So it's 3 dimensions. We have R1, R2, R3. Their components. Also, don't get confused if some books do it with a plus. Remember, you don't add them up. There's just to tell you that instead of comma, they're using a plus. I find it more convenient to have comma, but you can find it both ways. And what this is saying is that the moment is R is going to be the same, but the forces will be different because this angle, theta 1, theta 2, theta 3, theta 4, those angles are going to be different. So this cross F1 is going to be moment 1. Moment 4 is going to be R cross F4. So this will make it go clockwise. So F1 is going to be, this is going to be negative. This is going to make it go counterclockwise. So this is positive. And F3 and F4 are probably going to make it go clockwise. So they're negative as well. Okay, so if you notice, in 3 dimensions, it's going to be pretty tough, pretty difficult to find this angle. But the forces could be computed, could be measured with a sensor. So the distance is definitely, you can definitely find it because this distance is a linear distance. So you just go from the point that you're trying to measure the force at and on coordinate system that you're interested in, and it's pretty easy. So the blue line is a distance, has units of meters or inches or feet, and this has units of newtons. Therefore, remember the moment has units of Newton times meter. Okay, that's good to review. And as we said, you just go ahead and get the components and you can basically get the cross product. So this is what we just did. Okay, the other thing that we need to talk about is if you do not know the distance, you have to know how to find the distance. And the distance is very easy. So let's say you have a vector r, and this is x1, y1, z1. This point right here is that, and the end point is x2, y2, z2. Okay, so the distance in x is x2 minus x1. In y, y2 minus y1. In z, z2 minus z1. All right, if you want to find the distance r, which they're giving you, but at some point you might have to find it, we probably will have to find it. This is going to be probably need more room. X2 minus x1 plus squared. Y2 minus y1 squared plus z2 minus z1 squared. Got it. That is the distance r. And in this case, if you're doing, since you're doing the squared, it's a number. It's not a vector anymore. This is a number. So be careful. If they give you, I don't know, r is 10 meters, they're giving you just the magnitude. But if they're giving you 10, I don't know, let's do a better example. Let's say is 5 meters. That means that in x could be 3 and y could be 4 and in z could be 0, because 3 squared is 9 and 4 squared is 16. 16 plus 9 is 25. Square root of 25 is 5. So what I'm saying is that if they give you the component to get the moment with a vector notation, you need the components in I, j, or k. I means x, j means y, k means z. You need the components. But if they give you the distance, and say they give you the total force, then it's very simple, because the moment is 10 newtons times 10 meters, which is 100 Newton meters. But if they give you the force in terms of a vector and the distance in terms of a vector, what you can do is get the curl in terms of a vector. And if you need to, at the end, that curl, which we have over here, this is a component I, component J, component K. So at the end, if they ask you for the total magnitude, not just the components, you do square root of the component in I plus square root of the component in J plus square root of the component in K. And by doing the square root, then you can add them up. This is the total moment. Okay?